Today we're on page 28 of the Chemistry 1 Chapter 8 packet, and we're going to be talking about intermolecular forces, or IMFs. Intermolecular forces. Intermolecular forces are on this list on page 28 from hydrogen bonding down. So hydrogen bonding is an intermolecular force, dipole dipole is an intermolecular force, and London dispersion forces are intermolecular forces. So you have all these different kinds, these three. H bond is going to occur for compounds that have H attached to an F, O, or N. So you have to have an H attached to an F, O, or N for hydrogen bonding to occur. We'll see some examples of this on the next page when I draw the structures, but we'll give you the big picture now. So H bonding is when you have H attached to F, O, or N. A dipole dipole is simply for a polar molecule where you don't have an H attached to F, O, or N. And then London dispersion forces are for non-polar molecules where they are symmetrical in every way. So if we just take a look at our list, we can understand how to identify these, and then we'll talk about the specifics on the next page. So you can see here, water, H is attached to an O. Here, H is attached to an N. Here, the H will be attached to the O actually. Here you have the H attached to an O. These H's don't count right here. These H's don't count. It's only these H's that count. Okay? Here again, it's this that counts here, not these H's right here. So I'll actually, I'll just change that to an X over here. So these don't count, those H's. And then this over here, HF, you have an H attached to an F. Now, polar molecules, you could see, don't have an H attached to an FO or N. See, FO or N, this is not FO or N, it's just a BR. So this is just polar, 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 polar. All these are polar molecules. Polar, they're all not symmetrical. Whenever you have a bunch of C's, H's, and something with it, it's going to be non-symmetrical. If you drew all these Lewis structures, they would be non-symmetrical, so they would be polar. And then lastly, nonpolars, if you look at this plain old Kr, it's just going to be nonpolar, nonpolar. CCl4 is a tetrahedral. This is big linear. This is an organic with just C's and H's, so it's going to be nonpolar. SO3 is trigonoplanar, so is BF3. This is a linear. This is nonpolar as well. This is a trigonal bipyramidal, a big linear, square bipyramidal, and square planar. So all these are nonpolar molecules, and on the next page we'll see how to understand that from their Lewis structures. Now we're on page 29 of the Chapter 8 Chem 1 packet, and we're going to contrast two words, intramolecular and intermolecular. So intramolecular means within. Maybe you've heard of intramural sports. An intramural sport is a sport played within the high school itself. So we have Olympic volleyball would be an intramural sport because it's only Scotch Plains Fanwood High School versus Scotch Plains Fanwood High School. Ultimate Frisbee, we had a team here that would just, a club that would just play within our own school. Okay, but if you contrast that with our inter-school sports, that would be all our varsity sports that we play against other schools. So intermolecular means between the molecules. And this is the focus of what we're talking about in this chapter, between the molecules. But in order to understand the between, you actually first have to understand the within. So let's contrast that here. We're actually going to start with the ones we are talking about on the last page, which is water. So here's water, H2O. Now you know that when you draw a molecule of H2O, you're going to have an H connected to an O, connected to an H. It's going to look bent, even if you don't draw it that way. That's what the shape is because it's 4-2. You know that there's a polarity in this bond, so you can either do one of these arrows like this that we learned on the Vesper papers, or you could do a little delta negative and delta positive. And so you see that the O is going to be a little bit negative, and each H is going to be a little bit positive. All right, so that's shown on this diagram right here. Here's a delta negative, here's a delta positive of one water molecule. But remember, this bond is a covalent bond. Inside, that's covalent. So this is a covalent bond. It's polar, as you know. So the intra is a polar covalent bond. However, the between, which is going to come right here, is the H bond. So let's contrast that one more time. Inside the molecule, you have an H and an O sharing an electron, a pair, so two shared. It's a covalent bond, but it's not a fair share, so the O takes the electrons more, so it's considered polar. Now, because that makes this H a little bit more positive and makes this O in a different molecule a little bit more negative, they're going to attract each other with a weak attraction, which is called a hydrogen bond. So this water, one more time, that has a covalent bond here and here that's polar, causing this water to have a negative polarity here and a positive polarity here, allows it to attract with a hydrogen bond right here. And the same thing is going to happen right here and here. So all these hydrogen bonds are forming because the water molecules have inside them covalent bonds that are polar, causing these other delta negatives and delta positives to form. And so there's a weak attraction between water molecules. And that's what holds water together. So even though I'm calling this a weak bond, which it is, all these intermolecular forces are weak, H bonding is the strongest of the weak ones, which includes also dipole dipole and London dispersion. So H bond is the strongest of the weak intermolecular forces. When ice forms, you could see these hexagons are forming, and that is an orderly pattern of the molecules that line up. And you can see the bent nature of the water allows this hexagon to form. You can see these open spaces right here, and that explains why ice is less dense than water, because it spreads out, and that's why it'll float. So ice is less dense than water liquid because it's more spread out, whereas in this diagram you might be able to see that the water molecules are going to be closer. Here they're a little farther apart because they're spread out. And because they make these hexagon shapes, it's interesting that snowflakes have hexagon patterns, and every snowflake is different. There's a cool video to watch. The link is on the next page. Okay, let's continue on and now contrast this with dipole dipole. Dipole dipole is actually the same basic idea as H bond, except it's not going to be H with fun. So you're still going to have a polar molecule that has a plus end and a minus end, and another one has a plus end and a minus end because they're polar. And then this little attraction here is called dipole dipole. So you could actually think of hydrogen bonding as a special case of dipole dipole, but it's a stronger case. And that helps you to understand this graph coming up right here. If we're going to look at boiling points of different substances, so I'll write that over here just to help you understand. Okay, boiling points of compounds, I'll just say. There's a reason why these compounds have been picked. If you look at your periodic table, if you have it handy, this is H2O, O is in group 6. H2S, S is in group 6. H2SE, SE is in group 6. And H2TE, these are in group 6. We see an interesting pattern that water is the highest out of all these, but then these are increasing in their size and increasing in their boiling points. So let's talk about why. Water is H attached to Fun. So this is going to have H bonding. All right, H bond for water. Now, if you draw the structures of these, you saw the drawing of water, which I'm not going to redraw. Whatever. I'll just redraw it again. Here's water, H2O. You see it's bent. You would have the same exact Lewis structure for H2S, H2SE, and H2TE, except this would be a different atom. But they're all going to be bent. They're all going to be polar. Since this one has H with Fun, it's H bonding. But since these others do not, these are all going to be dipole dipole. So these have dipole dipole. And when you have dipole dipole, how to compare different dipoles together is by their size, and we'll see why that is in a minute. So this is a smaller atom, medium atom, larger atom, so these all increase in size. So the one with the biggest size is the highest boiling point if you're comparing dipole dipole. So interestingly, in this graph you could see that hydrogen bonding is going to be true for water. It's going to be true for HF because it's with FON. It's going to be true with NH3 because that's with FON. So each of these is a H bond, intermolecular force, higher boiling point compared to all the ones in their groups that are analogous, and these are all polar. Okay? The reason why they're all polar, we'll look at HF, see how HF is not going to be symmetrical, so that's going to be polar. It's going to be, and the other ones are going to be dipole dipole. And NH3, you could see that one is also polar. This one happens to be FON because it's attached to N, but all the other ones are going to have the same polar shape of trigonal pyramidal. So all these ones in green are going to be polar and dipole dipole. HF, all the ones in red are going to also be polar and dipole dipole, but these three are H bond. Okay, lastly, we're going to move on to what about nonpolars. So nonpolars have something called instantaneous dipoles, and let's just take a quick drawing to understand that. Okay, we're going to talk about CH4 first. So here's CH4. You look around the center and it is not different. It is HHHH, not different, so it's nonpolar. So here's our electron cloud. Let's take a look at, let's take a look at this. Okay, I'm just going to loosely interpret the electrons as this. Okay, the red cloud. So it's nonpolar because it's perfectly symmetrical. However, in one moment of time, this cloud could shift over to the right, just for a split second. If that happens, then this end is going to be a little bit negative, and this end is going to be a little bit positive. Well, what that is going to do is going to affect another methane molecule, CH4, that's close by. So this methane also has its regular nonpolar cloud, but if this cloud right here, the red, moves over to the position of the green, then this cloud, which is negative, is going to repel this other negative cloud and move it over as well. So this cloud is going to move over for a split second and become a little bit negative here, a little bit positive here, and look at what you got. You look at this interaction right here is going to be a little bit attracted. Okay, but it's not as strong as the permanent dipoles that we had before. Okay, so this is what we call an instantaneous dipole. Instantaneous dipole. Instantaneous dipole. Or you could call it an induced dipole because induced means you forced it to happen. So it's also called an induced dipole. So again, it's not a permanent one, it's just an instantaneous one because in the next second, this green cloud could shift way left, which will push this one way left, and all these instantaneous dipoles will have weak attractions here. So let's talk about methane. You know methane is a gas at room temperature. This is what comes out of our Bunsen burner jets. And we're going to contrast that with something else. Let's contrast that with another molecule that's much larger than that. And let's just go to octane. Octane, the prefix oct means 8. So 1, 2, 3, 4, 5, 6, 7, 8. Now octane, it's going to have all these C's and H's all around it. Okay, I'm not going to bother drawing all the H's, but these are where they would go. And then this has a cloud, roughly, of all the electrons right here. Okay, now for a split second, that cloud could shift down, and so it's going to be a little bit like this. So then this would be a negative, and this would be a positive. And again, that's going to be an induced or instantaneous dipole that'll induce a dipole in another one of these molecules. So here's another octane. You've probably heard of octane when you go to the gas station. This is in your gasoline, and it's a liquid, because you know when you get gas at the gas station, it's a liquid. So right away you know that a liquid sticks together better than a gas. So here's octane, which is a liquid, and that instantaneous dipole up top is going to push this one down a little bit. So this one's going to be a little bit more positive over here and negative over here. And this is where you're going to have your dipole, your London dispersion forces. Okay? So these are London dispersion. Dispersion means kind of like spread out. And forces, we call that LDFs for short. And that is based on, again, instantaneous dipoles or induced dipoles. So the point of this is, if you're nonpolar, your cloud shifts a little bit instantaneously, becoming polar just for a fraction of a second, and these weak interactions are called London dispersion forces. If you're a small cloud, you have weaker London dispersion forces. If you're a big cloud, you have stronger London dispersion forces, which explains why methane is a gas with weak forces, doesn't stick together well, and octane, which is in gasoline, is a liquid, and it's strong because its cloud has stronger instantaneous dipoles. So now we're going to wrap it up with this last graph. These are all nonpolars. You got CH4 going down the group, SiH4, GeH4, and SNH4. Notice that the CH4 is not higher up like these were because this does not have hydrogen bonding. So it's not stronger than these at all. In fact, they're all weak, and they're all going to be London dispersion forces, so it makes sense in this graph that CH4 is the least, followed by each of these with the increasing size. And this will help you to do the worksheets for homework.